you're changing every one of them, right? So be really, really careful about that. That's one thing. The other thing is for the trigger person. Now the trigger pressure is on the trigger person to be consistent and rapid. Don't be slow. It's got to be a quick shot in, and I go back and forth on this thing a few times here, like that. I just don't. It's not a one-time shot. Why? Because mixing is crucial in this thing. So I go like that, and then you see what I mean. In other words, it's open. I have the enzyme here. The tip goes below the nose. I seal it. Mix 1, 2, 3, and put it in less than 5 seconds. Don't say 30 seconds. Don't say 20 seconds. Don't say and then go in. No. It's got to be fast and deliberate. And then you can catch those early time points. Now, let's talk about some of these early time points. I have then on sheet 3, and I think that you have sheet 3. That's not a good print. Yeah, that is. But the point about sheet 3, look at this. Sheet 3 is after you've done that collection on sheet 1. The data collected, raw data, as you're writing it, as you're keying it in, is on sheet 1. Now sheet 3 is this is how the result page will look back at me. Right. Now, I also warn you that I got lazy. I didn't put all 5 tubes in here, 1, 2, 3. There should be, you're supposed to have tubes 2 through 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. See, so there should be 5 curves out there like that. So we're expecting back the raw data. Then we're expecting back these graphs. And then it gets complicated because from there you have to then construct curves based upon this. These are smart cells over here. Rajiv, these are smart cells over here. In other words, these cells are watching what you're putting in here. Yes. These cells are watching what you're putting in. They will change and update as you put in your data. Why? Because you can these 3 sets of data will give you a Lineweaver-Burke plot. Yes, they will. Or, so in other words, it is sitting there waiting for you to create. So you create graphs. Again, you go to insert graph, scatter, blah, 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 and it says what's your X range, what's your Y range, and you give them that data right there. Now, may I also advise you that you have to watch these like a hawk in terms of the mixing and in terms of, because each one of those should be in order of decreasing optical density. In order of decreasing optical density. So in other words, if you look at 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, they should be going down, 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 down. That's what these plots show. In other words, they go down, 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 down. That it needs to be done. Now, very frequently, through no fault of your own, because you are working with very high error since you have no temperature control in the lab. You have no temperature control, so therefore, very frequently, you may inadvertently have one that reads more color than it should have. In other words, it gets out of sequence. It can get out of sequence. It might give you more color than say, hey, wait a minute, that was supposed to go downhill. Show that to me, and we'll say we'll drop it. Just drop it. In other words, disqualify it. It was either a mix error, or a prep error, or it could have been someone got distracted and handed you tube 8, and they should know, but they handed you tube 10, some weird thing like that, okay? Or it just could be just the temperature fluctuation in the room. Temperature fluctuation in the room will give you a lot of error. So therefore, it's not uncommon for someone to say, oh look, this tube 8 got out of sequence with tube 9. Now what do we do? Answer, disqualify. one of them, so that you get the right sequence back again. Okay? You just take one out of the run. Pull them out. That's fine. But report all the data to me. But before you do the graphics, then you say, well, we pulled one out. Fine. That's fine. Perfectly legitimate. Whose is this? Oh, okay. Now, the rubber hits the road here on terms of the calculations. Now, this, we want people to work alone. However, this is a rather demanding experimental report in terms of how much material you have to calculate and prepare. Okay, now, so therefore, I think that it's only fair that the calculations on the Excel be shared, work that jointly. Everybody work together on it. Because that's a lot of data, a lot of graphics. A lot of graphics. Let's show just one typical case here. Let's just look at tube 6. Tube 2, I'm sorry. Here's tube 2. And it goes like this. This is absorbance, and this is time. From this one trace here, you are asked to give me back a rate. The rate, which means rate equals slope of a linear regression. And that equals velocity of the enzyme. Turn on all of the spectrum colors. Okay, now be careful on this. This thing, the smart cells over here are watching, and they will give you. See, it says slope on there. I think you see a slope, right? This is on sheet 1. Substrate, you get used to this. Substrate is also corresponds to tube number. Yes, substrate is also corresponding to tube number. Tube 2 is 2.5. Tube 3 is 1.5. Tube 4 is 1. Tube 5 is 0.75, etc., etc., etc. All right. Now, these smart cells over here do the following. But this is up to you. This is your baby. So this is what you do. The cells over here are looking. They're watching you. And they say, okay. And what the cells over there are taking, they're just grabbing the first initial times. Because if you take these, that slope is going to be quite flat, don't you see? Right? Actually, it can be done either way, but think it through carefully when you're doing the Excel calculations. So that for each tube on the smart cells, you will see then over here, 2.50 is tube number 2, and it will give you a rate like that. Or you can calculate your own rate. If you say, I don't like his smart cells, I don't know what's going on there, I can't see them. Then just take your own data and do it yourself. There is a command. You can do it by plotting it, or you can command it. I believe that the command in Excel is called linest. It's the Excel command. You can open up my smart zones and look at it and say, what was that command called? And I think it's called linest. But for each tube, you have to calculate a rate. That's my point. Okay? Tube 2 to 6, tube 7 to 11, and tubes 12 to 16, you have to calculate a rate. This is going to be a very, very, very busy one. You really need to do this together. Don't try to do this alone. It's too much work. Too much work. Okay. At the end of the day, then, you will have a table. So I want you to give me the plots as I have there on sheet 3. I want those back on results. Then you can give me a table. And the table looks like this, results. And a table. So we'll have a table. Table 1, 2, 3, I don't know. It could look like this. It could look like right? This is substrate. This is rate. This is one way to do it. Each person has a different sense of organization. But it could be slightly different from each one, okay? So you could have, for example, it could be like this. 2, 3, 4, 5, and 6. Here it is. 2, here it is. Look, this is 2, 2. This is 3. This is 4. This is 5, and that's 6. Okay. And that means that over here you have no inhibitor. And so we can see the rates. You can see a rate here, a rate there. So this is XXX. This is YYY. This is ZZZ. And so on. Okay? Got the idea? Now, over here, then this is, let's say it's MTG. Again, you have tubes 7, 8, 9, 10, and 11. And then you put, it's the same substrate concentration. 2.5. What did I just say? 1.5, 1.0, 0.75, and 0.5. Yeah, and same thing over here. 2.5. See it? 1.5. You can organize it how you see fit. The point at the end of the day here, then is we have, these are X1, 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 Y1, Y1, that's just a rate. And so on and so on. So there are 5 rates here, 5 rates there. And here's the last one, which is MGP. MGP. Okay. These now, you can command on Excel. This is a real workout for you on Excel, what to do about this. Here's the workout now. You have to take this data and then you have to invert it. Yes, you do. So this is table 1, or table X, and then here comes table Y. Over here, watch this. Table Y, or you could put it, conceivably, you could make it all in one, but it would look like then this. It would be 1 over substrate. Yes, it would, and 1 over the rate. Okay. That's 2, 2, that's 2, 3, that's 2, 4, that's 2, 5, and 6, right? 2, 3, 4, 5, and 6. I'm not doing a good job of this, but you get the idea then. So for every element in this table, you have its inverse over here. The inverse of 2.5 is what? 0.4? What is 1 over 2.5? Quicker. 0.4. Rajiv, help me out. Okay. What is the inverse of 1 over 1.5? 0.7. Thank you. 0.7 something, right? What's the inverse of 1 over 1? What's the inverse of 1 over 0.750?
$1.5.
Yeah, something like that. It's got to be a